Okay. So despite we use carbonate for almost everything, and we saw that this kind of relationship last year as well, I thought about really a quick recap of some exercises with the 1-3-1-5, and then the next hour 1-2-1-4 and 1-6. But the 1-6, honestly, it's rarely used. It's a very, very specific one. If you see it and you want to use it, absolutely do it. But I would say that the most common ones are 1-3 and 1-5, like carbon relationships we want to consider. Between the 1-2-1-4, probably the 1-4 is the easiest one to use. The 1-2 is one of those that use it only if it's really, really necessary, or you think it's really necessary. So it's like when you do nucleophilic aromatic substitution, don't do it unless you are absolutely sure that there is no other route. 1-3-1-5 are the easiest one. When we talk about 1-3-1-5, what I mean is, if you have two carbonyls in one molecule, distant 1-3 or 1-5, use it because, or at least consider use it because it simplifies everything. Even if you don't have a 1-3-1-5, think about maybe there is a double bond which might come from a hydroxyl group, which might come from the reduction of a carbonyl. So also the carbonyl hydroxyl could be a relationship 1-3 or 1-5, especially 1-3. So whenever you spot something like that, think about using it because it really is. If you look at the disconnection approach, there is a big part on this because it actually helps. So these ones are normally the 1-3-1-5 are normally the ones which are considered the natural, the logical dicarbonyl relationship. We will see later the 1-2-1-4, which are considered illogical, but actually they're not that illogical if you know how to use them. Only one of the first rules when you see a molecule, okay, spot the functional groups, the different functional groups. Once you spot the functional groups, have a look at the potential relationship between different carbonyls because they are very easy to use. And especially when we saw that on the video, when we use the alpha protons on the carbonyl. So have a look if your carbonyl potentially has one set or two sets of alpha protons. That's really important because if you have two sets, you also need to consider either kinetic or thermodynamic, or you have to consider an activator to be specific, to be selective on one position. But there are basically two ways to use it, two main ways to use the carbonyl. One, if you want to use it, the molecule with the carbonyl as a nucleophile, you must have alpha protons. Because if you take it out with a base, it becomes a good nucleophile, a soft nucleophile, remember. So it does do the direct attack to the carbonyl, but if there is some, if you can decide between doing conjugate attack or 1-2 direct attack, normally a soft nucleophile prefers to go for the conjugated attack because it's more accessible, just that. Normally these nucleophiles are larger than others, than a Grignard, for instance, and the charge is quite spread all over it, so it's not concentrated on one carbon. That's why they tend not to do direct attack unless the direct attack is the only thing they can do. But either you use the carbonyls, taking out a proton as a nucleophile, or you use the carbonyl itself as an electrophile. So this is the way that you want to use the carbonyl. There are not many other ways. Yes, there is the ampolon, we will see. Then there are other ways to use the carbonyls, but normally speaking, Either you use it as a nucleophile, alpha protons, or you use it as a electrophile, something attacks it, okay? So when you use it as a nucleophile, always consider the enolate. And when I say consider the enolate, I mean, once you disconnect it, go for the forward synthesis and think about, do I have any problems? Specific regioselectivity problems, chemoselectivity problems, because of potential enolates. Think about, you saw that with Joel massively last year, but we always get back to the stuff. Do I need to tame the enolate? Do I need to activate the carbonyl in a way or another so that I'm more selective? Ask yourself these questions, especially when you do the synthesis. And I saw that on the workshop. Don't think about it. Write it down. Don't try to have everything in your mind. Write it down. Maybe it doesn't work. Cancel everything. Start again. Don't just think, yes, it might work this way. If it works with the synthesis, if you try to do the synthesis, even without doing the mechanism, but you see that there is not a problem, then I'm 100% sure that you're correct. So how do we use these relationships sometimes? If you have a negative charge, you can add the bromine, and that might be useful. Eventually, this one might be useful for the 1,4. We will see. This compound might be useful for 1,4. So you need to remember, how do I make it? Then you can attach anything with a good leaving group via typical SN2. So the negative charge attacks the backside of here, kicks out the halogen, and you get your new carbonyl compound. You can always attack another carbonyl compound. Again, if there is not a possibility of doing conjugated attack, let's say with a benzaldehyde, which is not enolizable, and the carbonyl of the aldehyde is quite electrophilic, this one indeed does the direct attack. All to the ester. This is the difference. The difference between the two is the aldol or the Claisen condensation. If you have the aldol, you get an alcohol. If you get a leaving group here, similar in the Claisen kind of condition, if you have a leaving group, you restore a carbonyl. So again, from the retrosynthesis point of view, if you need to have the two carbonyls, and if you disconnect this part, one of the two carbonyl compounds must have a good leaving group. It could be an ester, it could be a chloride, it could be something like that comes from a tosylate, a big bulky leaving group. Anything that has a good leaving group restores the carbonyl. Anything which doesn't have a good leaving group, let's say benzaldehyde, what are the potential leaving groups? Hydride or benzene carbonyl? No way. This one is going to stay as an alcohol. Again, think about possibility of tame the enolate so that you stop some potential side reactions. So this is all good material for how to use the alpha protons of a carbonyl. And again, I'll never get tired. Carbonyl is the most versatile functional group that you can use in retrosynthesis. Even if your molecule doesn't have a carbonyl, that does not prevent you from putting a carbonyl and then maybe remove it, because the carbonyl chemistry is really useful. Remember that these ones are also have other alpha protons that can be used for that in the next synthesis in this case, but coming from something else in terms of this relation. Okay. Let's do this one first. How do you disconnect this one? So what are the starting materials for this? Remember that there are different possibilities. Especially with the 1,3, you can cut here, you can cut there. They're probably, most likely, they're both correct. especially if you indicate the two potential starting materials. But normally one of the two is more likely to be used in the lab. So it's more useful, it brings less byproducts or less hassle because stupid purifications. So whenever you do this kind of stuff, think about grow it, try to do the synthesis, and also try to do the synthesis or the retrosynthesis first, and then the synthesis of what you obtain from the first disconnection. So if you disconnect in a position which leads to a very difficult starting material, try the other one. Maybe it will lead to something else. Maybe it will lead to something symmetrical. Maybe it will lead to something which you can spot immediately. I can do in this way instead of driving crazy. For instance, if I say A or B, which this one is A, where would you disconnect? A or B? B. Let's do B. So again, if you have something like that, again, you want to put the positive charge and the negative charge somewhere, because eventually the negative charge goes to the positive and it forms a bond. So you want to form this bond now. Where do you put the positive charge and where do you put the negative?
Yeah, positive on the ester.
Positive on the ester, negative here. Well, again, potentially they're all good. The symptoms, remember that the symptoms are fictional compounds. They're not compounds yet. So if you put the negative or the positive, you must put something that creates a negative charge or a positive charge. So you're not wrong. But most likely, this one comes from the cyclopentanone itself, because it has sets of alpha protons that can be removed. And this one instead must have a leaving group. It can be a chloride, it can be another ester. Does this reaction work in synthesis? You put a base. Maybe you need to tame this enolate because otherwise this one self-condenses. But that is something that you will do on the synthesis. For the exam, for my point of view at this moment, I don't care if you say, I just use a base. The base takes a proton, leaves the negative charge behind. And this one, at some point, and repeat, and it does that. That's okay. You could do it. There is a potential problem here. Finish spotting. It works. It's correct. But there is a potential problem. What's the potential problem, you think? A practical one that might happen in the lab when I do that.
Substitute on the end.
Absolutely. This is a living group, so this one. So it might happen again. You can have a mixture of dye attack, double attack here, and a mixture of starting material. The same way as when you use the Grignard reagent on an ester and you want to stop a ketone. It doesn't stop a ketone because the ketone is more reactive than the starting material. This is the same case. Each ester group brings a little bit of resonance. So when you remove this one and you create your ester group here, this ester group, your target molecule, is more reactive than this one. So you can have a potential dye substitution. So if you do this, it's good, it's correct, not completely correct, because you might have a potential byproduct. So normally, if you try this and you spot the potential problem, let's say that that one was an exercise. You might lose a couple of points because you didn't consider that. But it was still correct. But if you spot it, try to do the other possibility. It's a 1-3. There are only two possibilities. So you open this one. And then in synthesis, you don't have any selectivity problems, any double attack problems, because the first one ring closes selectively. This one, if it takes this proton from here or this proton from there, whatever starts first, it creates a 5-member ring and it stops. That's selective. Then you need to consider how to make this one. We will see later. This is a 1, 2, 3, 4, 5, 6, like 1-6 dicarbonyl relationship. We will see the next hour how to make this one. But this one will probably be the most selective route. Again, if you do the other one, there's no wrong completely. There is a good strategy, but you need to consider potential. That's why I keep saying, even if the retrosynthesis works in your mind, write down the synthesis, try to do the mechanism. If attacks here, can I get something else? If it does, you might want to reconsider. So this one is a Dickman condensation, but eventually they're all Claisen-like. All Claisen condensation, that if you want to remember the names, the aldol normally gives you the condensation gives you the alcohol because you don't have a living group. The Claisen condensation and Dickman is just a variation, must have a living group, so you restore the carbonyl. So in the aldol, you get, in this case, you will get a hydroxyketone in the same molecule. In the Claisen-like condensations, you always restore the carbonyl. So if I tell you this one, why would you disconnect? There is a 1, 2, 3 possibility, 1, 2, 3 possibilities. So 1, 2, or 1, 2 prime. Here you have to consider the symmetry, potential symmetry of the molecule. The top one. Why do you think is better than this one?
Because it's got carbon.
They're all carbonyl.
Yeah, but it's.
But if you cut here, in the next attack, you might have a proton which is very, very easy to be taken because it is in alpha to 2 carbonyls, so it's very acidic. And you need a good living group here. Also, the other one works, same as before, but think about the potential symmetry. When you have symmetry, and if you spot any symmetry, try to use it because it normally helps. It sometimes gives you one reaction instead of 2-3 steps reactions. So if you start from here, then you need to disconnect all the rest in another 1-3. Instead, if you start from this compound, this is as a chloride or as an ester, works the same way. As long as it's a good living group, it works. Then, of course, you need to keep disconnecting. But again, you can use the same trick. Disconnect here so that you have a proton on this molecule, which has 2 very acidic protons, easily taken by a base, which can attack this one via SN2. Again, whenever you see symmetry, use it because it helps.
So that's the 1-3 by carbon.
Mhm.
So what would be the other option to put? Because you always said there's like two, and 1,3-dicarbonyl.
They are both 1,3-dicarbonyls, only they are different 1,3-dicarbonyl in this case. Sometimes, depending on the rest of the molecule, could be another a variation of that. But this is 1, 2, and 3. This is 1, 2, and 3. This is again 1, 2, and 3 here. So they're all, in this case, they're all 1,3-dicarbonyls.
So why is that the point? Oh, for this 1,3.
Just because of the symmetry. So they're all correct. Only one probably leads you to multi-step synthesis. This one is that you use the symmetry here, super selective. Once you use a base on this compound, you take selectively only this proton. So it makes the next reaction super selective because this one cannot enolize. It's a good living group, you restore the carbonyl, and you do want the carbonyl. And the same happens here. You have this alpha bromo benzyl, but whenever you use, the moment that you use a base here, it selectively takes one proton, it attacks here, and it stops. Okay, so if you use a strong base and an excess, you might even think about going over and doing multiple attacks, but normally it stops there also because of hindrance. Then you isolate the compound, you think about you're in the lab, you isolate the compound, and you put it in a base and in the presence of a very electrophilic carbonyl, and then makes your target molecule. So if you start from this diester, this is a malonic ester. The base, this reaction is super easy. Maybe you don't heat, maybe you do it at room temperature. If you heat it up, it might attack again, but you need to push it because of the hindrance. Then you isolate it, you put it in base again. Even a soft base will take that proton and it will react with a very electrophilic acyl chloride.
Yeah. In exam, if I use a base, what am I doing?
If the strength and the hindrance of the base doesn't really matter, I'm happy with B minus. Doesn't care, doesn't matter. If your synthesis might lead to byproducts, let's say you have a possibility of 2 different alpha protons and you might want to play with, or you might need to play with a kinetic or thermodynamic, then in that case, I would like you to specify what base, because it might not be wrong as long as you use the right conditions. In that case, I need you to specify what base you will use and the range of temperatures you will use. If there is a possibility of kinetic thermodynamic product, B minus only won't do. Only in this case. That's why it's normally up to you choosing the easiest route. But if you have to use the strange conditions, they are not kinetic and thermodynamic, they are not strange, but if you can avoid the possibility of forming byproducts, try to avoid it, because remember that all this stuff that we're doing, to me, will be important if you're using it in a lab. So higher yield, easier purification, cheaper starting materials, they're all good stuff for a lab. What about the retrosynthesis of this one? How can you stop the reconnection after that? Where do you want to disconnect? You have 1, 2, and 3. Remember that we said that the relationship could be also with hydroxyl if it leads to the use of carbonyl. Where do you disconnect first? Because there are, again, you see a molecule that you spot functional groups. You have amino group, you have an ester group connected to the amino, you have this carbonyl, you have this hydroxyl, you have this phenyl group, which can be considered as a substituent. Phenyl group is a good substituent if you use it as a, I don't know, Grignard or organolithium reagent. So when you have so many options, think about what is the easiest of the options. What do you think you want to cut? Here. Again, let's try. I think you spotted the most difficult part, but let's try. So if you cut here, you need to put positive charge or negative charge. Positive, I guess you want to put it here. Negative is going to be there. Yeah. I wouldn't go too much further on this one because no, it's not. It's more difficult. It's not. There is not wrong or right here. Technically speaking, it's doable. I think it's more risky because you don't have a proper carbonite here in the other way around. So these protons are not as acidic as if this one was a carbonite. Because in this case, you might think you want to do an FGI, you connect this one to carbonite, and then you reduce it down. But actually, this one cannot go back to carbonite because it will have five bonds that carbon. So this reaction is probably not really feasible. But you see, technically speaking, it wasn't wrong. Then you try to put the charges, doesn't work. Scrape it off completely, and you try again.
What about the other side of the carbon?
We'll see. Here, even.
No, as in,
Here.
yeah.
Yeah, technically speaking, let's see what let's see if it works. In this case, you want to put again charge or negative charge on one side. Probably you want to put the positive charge here with a carbonite at big delta plus. You must have a negative charge here. Then you try to do the synthesis. Does this one work? Does not work. It does. That's okay. Now you need to disconnect this one. How do you disconnect this one? 1, 2, 3, 4. This one, this one, 2, 4.
Yeah.
Let's try. So, okay, so delta positive, delta negative, where do you want to put the delta positive? Probably again on the carbonyl, I guess. So you must have a living group, whatever living group here. The delta plus, and here you need to put a delta minus. How do you put a delta minus here? What do you need here to put a delta minus? Again, you try, you cut it, doesn't work, or it's not intuitive. Try again. Go back to the original molecule. So there is another option, of course. If it's not 2, 4, it's 2, 3. If it's 2, here, either you put the positive here and then negative there, or the other way around. What would you do? So the positive, if it's possible, always on the carbonate is the easiest way to use the carbonate. So in this case, you want to put a living group. Remember, whatever it is, it could be an acyl chloride, it could be an ester, but it must be a living group because in synthesis, you want carbonate back. On the other side, you got an alcohol side. It will work. So basically, this one is an esterification in synthesis. Okay. I would have done this one first and then treat it, but it works. It's the same way. How do you make this one? If this one comes from how do we make this one? Here. It's the right explanation, but it's not the right living group. There is an easier one. It's the oxide. Easy. Whenever you see carbon-carbon saturated in an alcohol, always think about the nitric side. With me, don't care about the potential, any potential racemications all around. Marcella taught you how to do these kind of reactions very specifically. But Marcella loves using the epoxides, and I do too, especially when you have this kind of relationships. So this one could be easily disconnected here, but instead of putting a living group there, the epoxide itself, when the ring is open, it's like having a sort of living group. I will do that, probably that first, because it makes all the rest of the reaction easier, but in the end, we didn't do this part yet. We could do this one. We should do this one as well. Normally, a good disconnection to go for ideally cheap and available starting material should go for no more than 6 carbons and no more than 1 functional groups. So 2 functional groups are already, of course, there's plenty on catalogs of bifunctional or 3 functional groups, but they might be more expensive. So you might want to keep disconnecting. This one can come from attack of an epoxide and then complete oxidation. Would it work? Or Grignard. How do I use the Grignard to make this one? How can I use a Grignard? Because this one can be done by epoxidation, attack of the epoxide ring opening, you get the alcohol, and then you oxidize that alcohol to carboxylic. But what if I tell you maybe the Grignard is the best option or the easiest option? How can I make carboxylic acid with the Grignard? I think we saw it on the workshop. How can I make from a Grignard a carboxylic acid? Form your Grignard, you bubble CO2. You get your carboxylate, and then you need to protonate it because the Grignard is strong basic conditions. Always remember to protonate it again. So for instance, this one can come from the Grignard here. In synthesis will be magnesium, THF, bubble CO2, second step, protonation. And you get your carboxylic acid. This one can come from, let's say, an alcohol, and then we can carry on. We can go easily to benzene. Let's say that the alcohol comes from an FPI. You get the carboxylic acid. This one might come from toluene, for instance. So this one, or the Grignard itself, and some more carbon dioxide. This one will make potassium permanganate. In synthesis, you make your carboxylic acid. This one, lithium aluminum hydride, for instance, you get your alcohol. This one with phosphorus tribromide or pentabromide, you get your bromo, magnesium, bubble shoot, carboxylic acid. Okay. This is if you want to go back to the easiest available starting material. This one will have 7 carbons, 1 functional group if you consider either the metal functional group or the phenol itself. This is toluene. This is super, super cheap. You do in the lab, you will never go back. Probably in the lab, you start from either the benzyl alcohol or the benzyl bromide. It still works, but here we're talking about the exam, or we're talking about retrosynthesis. But if you were in the lab, it will be super easy to do that. And this reaction, I promise you, this reaction, when the Grignard here, the normal CO2, takes selectively 100% your carboxylate and carboxylic acid. It's super easy. But again, you see that there are so many different options. So don't get stuck on what is your first thought. If you think about the disconnection, then you try to do the synthesis. You think it may be problematic. What if instead of getting a headache and try to fixate with that one, I cut on another carbon-carbon bond and see if it gets easier. Sometimes it saves you 15 minutes. Synthesis. On the synthesis, you might want to say that these two don't react as they are. Yes, on the disconnection, you get your carboxylic acid. But in synthesis, if you put a base here to do the attack, to take the alpha proton and to do the attack on the carboxylic acid, remember that the first reaction that occurs is the acid base. So if you put a base with these two, the base takes the proton of the carboxy, passes out as a salt, that it stops reacting. So in synthesis, you want to say that, like I always said, whenever you are in synthesis, you want to tell me if you need a protecting group or not. In this case, if you create an ester base, it is like using a protecting group of the carboxylic function. Okay. So groups and activators only in synthesis, forward synthesis. On retrosynthesis, I don't particularly care if you specify here. You can if you want, but I don't care too much if you specify here that you need then an ester instead of the carboxylic straight away. I don't care if you do that on retrosynthesis, but you need to tell me synthesis, because if you are in the lab, you won't react them both. You will go through the ester, then you use a base, you get your alcohol, then you will need to deprotect basically if you want to use the carboxylic acid, or straight away if you get this one commercial instead of going through the epoxide. You get the alkoxide, the attacks your ester, and you install the carbonyl which you need. So that will make your target molecule easily enough. 1,5, sorry for that. I'm done. 1,5. Sorry. I need the voice to come back. I promise you, it's not cold. 1,5. Again, two possibilities. Disconnected on that side or potentially on this one. What you need to remember from the 1,5 is that you need the alpha beta unsaturated carbonyl. And you need to make conjugate attack on that. Whenever you need an alpha beta unsaturated, normally, it's not always, but normally is because you want to do conjugated attack on the double bond. Normally. So that's good strategy. Tomorrow we'll do only exercises with everything all together. And we'll see exactly what I mean with strategy. So when you have this one, if you need to put a double bond somewhere so that you create your alpha beta unsaturated, again, if you have two possibilities, think about the easiest one. So if you got here, you get this compound, which is nice and easy, and cyclohexanone. If you cut on the other side, you will get the double bond on the cyclohexanone here. And then it's doable? Yes. Convince me. Do the retrosynthesis of that. It is doable. So if you carry on doing it and you disconnect it perfectly, you get full marks, exactly the same as someone else starts from the easiest position. I don't care, but it has to be correct. So the synthesis, you might want to use LDN and then 10-dienolate. Again, this is from the synthesis point of view. You probably, I will not ask you to tell me exactly this one, but if you are in the lab, you need to consider it. So I always try to take all the possible tips, because eventually the retrosynthesis, someone asked me in the past, but do you really use retrosynthesis in research? I will say that anytime you think about a molecule that is not already in the literature, you have to do your retrosynthesis. If you want to do it straight away, because you imagine immediately the starting materials, you're still, in your mind, you're still doing the retrosynthesis. If you can do the retrosynthesis using these tricks, these procedures, this systematic approach, then you just have advantages. In this one, you do conjugate attack. Remember that all the enolates that come from removal of alpha protons gives you all this enolate gives you a good soft nucleophile. If you have the chance to do conjugate attack, that will do conjugate attack first. It will never attack straight away the carbonyl. Plus, in this case, the carbonyl is an amide, so it's even less electrophilic. But even if it was a ketone, it will go for the 1,4 attack. If you have, for instance, if it's unsymmetrical, you have an emitter here. This is a reaction that you did in the lab, connected to thermodynamic conditions. In this case, you need to, this is one of the cases where if you do that, you will need to tell me what base and what conditions. In this case, B minus only won't do. If you have to do this kind of reaction, especially if it is unsymmetrical, please try to specify the base that you're going to use. Here I use LDA without the metal. It doesn't really matter because either attack, there is not a kinetic thermodynamic on the cyclohexanone. This is a little more difficult, and I think we will stop at some point, and then we'll do the 1, 2, 1, 4 in the next hour. I think we'll do this exercise. I don't know if I have any more. I probably do, but any other exercises? There is nothing new you can use for practice at all. Let's focus on this one now. What would you do? You see some molecules like that, they start becoming bigger molecules. But I can tell you that you can do anything here with carbonyl things. You have 1, 2, and 3. di-carbonyl relationship. You have an ester, and the ester is a CO disconnection. You have these double bonds, which can be broken here. Remember the double bonds? Whenever you see a double bond, you can think about something which had an alcohol, which might come from a carbonyl. Or when you see a double bond in a cycle like that, you can also think about a Diels-Solder possibility. So you have many options here. Where do you want to start? Remember that the easiest thing is try to start from one position and see what happens. I can tell you, you might want to start from straight away the easiest carbon heteroatom disconnection. But in this case, I would probably prefer to keep it. Think about the symmetry. If you take out this one, you start from the carboxylic acid. If you start from the carboxylic acid, you have the acidic function. In the rest of the reaction might mess up. It's doable? Yes. Is correct? Yes. You start with that and you get stuck, you get the good marks for this kind of disconnection. But you'll probably get stuck. There is a 1-3 relationship. You go open here. But think about it. If you open here between 2 and 3, you have a massive open structure. You don't have any symmetry, you don't have anything to play with. So that further disconnection becomes also a little more difficult than you would expect. What if you cut here? Can you see symmetry all around? So I can tell you that if you cut there, and you think about this one, might come from a former OH, which might come from a former carbonyl, that really helps. Whenever you see double bonds, think about putting an hydroxyl here, which might come from a carbonyl. And then you need to have something which attacks the carbonyl there. Can you do that? Easily, because you're from a 6-member ring. That is, in retrosynthesis, is the opening. In synthesis will be a Robinson undulation. Robinson undulation creates 6-member rings exploiting the carbonyl. The alpha protons on one side and the carbonyl on the other side, that then eventually makes this kind of. But even if you don't remember the name Robinson undulation, you might want to see. We saw a lot of cyclizations. Whenever you have cyclizing making a 5 or 6-member ring, it normally does it. So if you find anything that forms a 6-member ring, that's a good driving force. So your disconnection is going the right direction. So if you open it, what if you open it, you get this one? Can you see symmetry as well? Where will you cut now? Again, it's tempting to cut here. Don't. Because it works, but then you come up with a carboxylic function, which is more difficult to handle than an ester. You saw it before. You needed the carboxylic function. Eventually, in synthesis, you need it for the ester. Because of that acidic proton might mess up with your synthesis. So here again, 1, 1, 2, and 3. Okay, you can cut here, you can cut there. But what if you cut here instead? Symmetry again. In this case, you're doing 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Again, symmetry. In this case, you use the typical 1-5. You need to have a double bond. And if you want to have a double bond, if you choose it rightly, if you use it wisely, clearly, sometimes it's mandatory. You can form a double bond here, but if you cut there, well, you can form a double bond there and use it as well, but it's going to be messy. You can do it. It's not mandatory, but you can do it. So technically speaking, you can do that. No, actually you can't. Because, yeah, if you cut here, you have and a double bond. Yeah, that will do. But it's gonna be complicated because then you need to do the retrosynthesis of this one. One ester, two carbonyl, other carbonyl, then you have 4 functional groups in a molecule. You're not simplifying anything. You're making it more complicated. So try to use the symmetry. Yes. If I have to use one of the 1,5, I will cut here. And you will get your double bond. This one with a base selectively takes this proton. You don't have kinetic or thermodynamic problems. This one will attack. Okay. Then in synthesis, this one goes back to carbonyl and it tautomerizes. This double bonds, this is something that you want to know as well, because sometimes this you need to create the alpha beta unsaturated compounds as well. It's not finished. This one also needs to be disconnected. Double bond, again, it might come from a former hydroxyl group. You cut the double bond. You can do that if you really want. You can do that in as a VTIC. But if you get the halving, and you think about using this one for the base, which attacks the halving, nice and easy. This one cannot analyze. This one cannot analyze. This one has an alpha proton. This one doesn't have an alpha proton. You attacks here. You get your alcohol. Warm up the reaction. This double bond conjugates with this phenyl ring, this carbonyl, which is conjugated with this other one. I would say that it's almost impossible to keep the alcohol in this position. It will dehydrate spontaneously because of the whole conjugation. It's the same way as if the carbonyl, if there is a chance to go back to carbonyl, normally it prefers to go back to carbonyl. The same way, even with stronger problem in this case. If you can conjugate something, it will conjugate. So the chemistry is always the same. Only in this case, you are mixing up a little bit of 1,3 and 1,5. Here, this one is basically a 1, 1, 2, 3. You just don't see it immediately because there is a ring. But actually, there is a 1, 2, 3 relationship. You have here, and then you do the synthesis. In the synthesis, from the synthesis point of view, this one is selected. You can take protons only from here. Yes, this proton is more acidic, but you form 1, 2, 3, 4 member ring instead of a 6. It will never form. You will never take this proton. So if you put a base, the base might take this proton first, but it won't do anything. At some point, you take also this proton. You attach the carbonyl, intramolecular cyclization to make a 6-member ring. Nice and easy from the kinetic and the thermodynamic point of view. Dehydration as well, because also here, conjugation. It's almost impossible to keep the alcohol there as well. And then you do your 1,5. And just remember, there are different possibilities to cut the 1,5. Choose the one that gives you the easiest synthesis. I don't know if I will do this one. Let me check. It's probably easier to stop here. This other exercise is only for practice. Yeah, I have only this example left. for practice, and then we'll do a break, unless you really want to do this one. I guess not. But this one, again, feel like it's really easy. Then think about the synthesis as well, because even if it's spot symmetry, sometimes it's back and forth, back and forth, back and forth, and you really need to think if it really works or not. So maybe in this case, you want to use this one, that attack by the Fenner group in a way or another. So in this, maybe if I have to do this one in the lab, I will do diazonium. But practice. Have a look at home. Let's make a break, and then we'll do the 1-2, 1-2, 1-4. We'll do 1-6 as well, because they can be used. But actually, I will say that let's restart. I will do the very last part of my, let's say, systematic approach to retrosynthesis. So tomorrow we'll do only exercises using a bit of everything. But today, this is the very last part of the carbonyl chemistry that I would like to recap, because again, it's nothing new for you. All the synthesis, all the reactivity of the compounds are always, is always something that you have seen already. Only we're using it for retrosynthesis and then forward synthesis. So these ones are the illogical. Again, illogical is a bad word. Instead of illogical, maybe you'll say I'm not really intuitive sometimes. Because it's actually logical. If you need to use it, you can use it, it becomes logical. Sometimes they're not really intuitive. 1-4 is far more intuitive than the 1-2. On the 1-2, there are not many options. Normally, either use cyanide or ampolong. There are not many other options. So also that one might become logic. But these conditions normally might mess up with the rest of the retrosynthesis. So use them only if you think you really need it, like the SNR. Remember that the reaction could be, the relationship 1-4 could be also carbonyl to hydroxy, not necessarily carbonyl to carbonyl, because maybe that carbonyl hydroxy comes from another carbonyl before becoming an hydroxy. The 1-6, we will see at the very end, this is what we call the reconnection. So you start from a 6-member ring and you open it. But let's do bit by bit. The 1-2 symptoms, you want to put positive charge and negative charge in either one of the carbonyls. So one of them doesn't use the natural tendency of the carbonyl to be an electrophile. You need to turn it into a nucleophile. Either you do that with, we saw that with the rest of the lectures, with ampolong, inversion of polarization is the word for ampolong in German. Either you do that or you use the cyanide. You actually did the cyanide, the equivalent of the cyanide in the lab. Let's say that you want to do something like that. You have a 1-3 relationship between the carbonyl of the carboxylic groups, and you have 1-2 relationship between one carboxylic group and the hydroxyl. So if you want to do the 1-2, you need to put in either carbonyl, either the aldehyde over there, or the one that gives you the other carbonyl, you need to put a negative charge, which normally is not something that carbonyl really like to do. But if you want to carry on with this one, it's an easy 1-3 relationship. And you can start with this aldehyde and these alpha protons. Remember, this one is a proton. So you might want to make an ester in forward synthesis only. But this is the one we are interested in now. we did say, how do you create carboxylic groups? If you need to create carboxylic groups, there are, I don't know, R and PBr with CO2, and then protonation, and you create your RCOOH. But another easy way is RCN, hydrolysis, and then protonation. If it's basic hydrolysis, for instance, RCOH. Now, this one, the way to insert the nitrile is normally using a nitrile salt. Sodium cyanide, super toxic. Copper cyanide, I don't remember if I was talking about that with you guys with the second year. This one, I can eat it without dying. Please don't do that anyway, just in case. But the copper cyanide is far less toxic than the sodium or the potassium cyanide. But on the paper, if you have to use it at the exam, use sodium cyanide as much as you want. The paper is never toxic. Well, don't eat it anyway. Oh, this one, for instance, can come from Grignard plus CO2 at some point to make the synthesis. But let's do the 1,2, because at the moment we are interested more in the 1,2. This is the 1,2. You use the cyanide, it's a very good nucleophile, it attacks your carbonyl. You don't have a living group from here, on here. You never have a living group, so you get your alcohol. Only you get your this one is called cyanide ring. It's a compound which has an alcohol and the same carbon as of nitrile connected to it. You can hydrolyze now this nitrile group to eventually get your carboxylic acid, your extra carboxylic acid. Of course, we were saying we start from one of the carboxylic acid has to be protected. And the easiest way, if it doesn't mess up too much, the easiest way to protect carboxylic acid is to make the corresponding ester. So the bromide could be an organolithium as well, but in this case, you follow your Grignard. Could be organolithium, Grignard, CO2, bubble, protonation, carboxylic acid. Now you need to protect it because the next reaction will be susceptible to the presence of this proton. You do your next 1,3, that's an easy 1,3. You need this aldehyde. This aldehyde will never leave, so you need another living group on your aldehyde if you want to keep the carbonyl. Once you get the carbonyl, you get the aldehyde. In this case, whatever attacks the aldehyde will leave your alcohol. It will not attack the ester because the aldehyde is far more electrophilic than the ester group. So this reaction is quite selective. Of course, you need to protonate it because this one is a base, you get your alkoxide, protonation will give you the alcohol. Now, you can hydrolyze the nitride to the corresponding carboxylic, and you have your target molecule with 2 carboxylic acid eventually, and your alcohol. This is the 1,2 relationship. This was, if you consider this one as a carbon 1, 2, 3 relationship. So you use them both. Of course, you need to deprotect. And the deprotection here is just hydrolysis of the ester. That will not mess up with your reaction. So think about, whenever you do retrosynthesis, always think about 2 or 3 steps ahead. So will this reaction that I'm using, will these conditions that I'm using mess up with the rest of the molecule in forward synthesis? If it does, either you protect something or you cancel everything, you start from a different carbon-carbon bond or carbon-oxygen bond, whatever. Anyway, you change your strategy, because remember that also if you can avoid protection and the protections, it's always better, because not always protection and the protections are as easy as they look. I'm not going to take too long on the hydrolysis of the nitrile, hopefully you remember. But again, you will not be asked, neither from me nor from Marcella. You will never be asked the mechanism. I'm using it just so that you remember that the nitrile can be easily used for to make a carboxylic function. Okay. Eventually, you start from the nitrile, you end up with the carboxylic acid. Only remember that there is this carbon. Sometimes people forget, I keep saying, sometimes people forget that the nitrile contains already a carbon and they add an extra carbon in the target molecule. So they end up making up a carbon which comes from God knows what. How do we use, you're okay with this one? It's all in the slides, and then the slides will be in Canvas as soon as I finish. But how can we use, why do we think sometimes are useful this 1,2-carbonyl? This is a reaction that at this moment, if he's not doing it now, we will be doing very soon. Peter, master student in my lab, to make hexaphenyl benzenes, you have to start from the cyclopentadienone. It sounds like a big bulky molecule, but in actual fact, you just cut here and cut there, symmetry again, and you start from your 1,2-bicarbonyl plus this acetobenzyl, alpha protons, acidic attack, aldol attack on that, dehydration, and you get your cyclopentadienone nice and easy. This is a fantastic compound because it's super conjugated and it's between dark purple and dark blue. So it's not the kind where, this is what I keep saying to Simon, for instance, who says, oh, organic is so boring, it's all white. No, this one is not white. If you get it white, it's wrong. This compound is not a cyclopentadienone, whatever the substituent that you put around, and I do put substituents around according to what do I need in my monomer. They are highly colored. You get it white, it's not the right stuff. Easy. This one can come from symmetrical synthesis, symmetrical attack of 2 green reagents to 14. Again, 14 is super toxic, but not on the paper at the example. Please use it. Would be even better if you use the corresponding diester, the autoformate. It's less toxic, but still it's quite toxic because it's quite reactive. Remember, whatever needs to be reactive, if it's super reactive, it reacts with everything, sometimes with your DNA. So don't use anything which is dangerous unless it's really needed to. But what about the di-carbonyl? How do you make this di-carbonyl? This one is called benzyl. You used it in the lab. You made it in the lab. Anybody remembers how you make it in the lab? Yes. How can you make the two benzaldehyde reaction if they are both electrophilic? The thiamine chloride, what does it do to one of them? Okay. Unpolar. All correct. Perfect. So also in this case, if you need to do the 1,2-dicarbonyl, you have to do the unpolar in a way or another. You can use the nitrile again, but as a good substitute of the nitrile, we use the thiamine for the specific reason you don't want to use the nitrile, the cyano, the potassium cyanide or the sodium cyanide. You use the thiamine which works exactly the same way in terms of polarity, but it's so much safer. We will see. But if you want to consider from the retrosynthesis from the example point of view, please use potassium cyanide as much as you want. This is the reaction that eventually the thiamine does the same. So again, like we saw before, easy as that. Nucleophile attacks the electrophile. This one goes down. Hydroxyl group. Base, take proton, you create your nucleophile. That's the unpolling in this case. Because now this carbon used to be electrophilic. Now, because of the cyano group, becomes nucleophilic. That's the unpolling. Don't think that the unpolling is only the one with the polycyclic reaction with the di-carbonyl. Anything that inverts that nature of the carbonyl from electrophilic to nucleophilic is basically an unpolling. The thiamine one is an unpolling. So once you get your nucleophile, your former carbonyl attacks the other carbonyl of the benzaldehyde to form your hydroxyl compound, keeping out the cyanide in the end. You need to oxidize this one. You remember what did you use to oxidize this one in the lab? This is very easy to oxidize for a very good reason. If you say oxidation will do, this is one of the cases that I don't care if you tell me in specific, because any oxidant will do. Why do you think it's very easy to oxidize? What's the magic word when you use aromatics? Conjugation. If this one now is not conjugated. If this one gets oxidized, conjugation. Everything is conjugated. Remember, chemistry always wants to go to the lowest set of energy. The conjugated one will be the lowest set of energy of this molecule. So this one is reactive. Any oxidant, you can isolate this one, but any oxidant will turn it into the corresponding benzyl. And then your benzyl can be easily used with a set of benzyl on the top, or if you want to call it diphenyl acetophenone. Anyway, this one, aldol condensation, nice, deep purple, cyclopentadienone. Happy to do another reaction that I really like Peter to do that in the lab. Diel solder is an alkyne. We will see in another moment. That's for another. That is for another. I think I have it in my last workshop. We'll see. Anyway, remember this reaction? Yes, we said that. That's the timing. It works exactly the same way. This part especially, eventually, is nucleophilic enough for this carbonyl here, and you lose some big bulky thiamine here instead of the nitrile. But the most important thing is that this thiamine is far less aggressive, toxic than the cyanide itself. Although, again, if you use copper cyanide here, will do. But thiamine, you did it in the lab. You know that it works well enough. That's typical benzoin condensation, because the benzoin is in this compound. Then you will want to oxidize it to benzyl if you want to do the aldol condensation on the top. Remember the use of this kind of use of di-functional compound relationship. It's probably easier that you're gonna use the 1,2 as a alcohol, keto alcohol, than as a di-carbonyl. But again, if you want to do that, you need to create your negative carbonyl. And if you want to use that, we were saying, if you want to use it, a good way to do the unpolling is the Corey-Seebach reaction. Corey-Seebach is the one that you protect the carbon as the diethyl. Then you need to use Bewley eventually to remove this proton. Then your former carbonyl delta plus becomes nucleophilic one with the delta minus here. So basically, always think that you need to move from a delta plus to eventually with Bewley. Bewley will have a negative charge here with a negative. Then you attack your carbonyl. Eventually, this, if you want to restore the carbonyl from the Corey-Seebach reaction, you use mercury salts or mercury oxide. So mercury oxide will do, mercury fluoride will do the same. That's really good. This is a reaction that you want to remember also whenever you need to go back to carbonyl from a protected carbonyl, in case your other conditions are susceptible of base or acidic, because this one selectively they protect the diethyl using the salt or the oxide. But you don't need to have particularly acidic or particularly base conditions. It's quite neutral. Again, strategy. You need to protect a carbonyl, you think about immediately think about the diol, but the diol has to be deprotected in mild acidic conditions, but yet acidic. What if you have something like another hydroxyl group that dehydrates because it conjugates? You don't want to use acidic conditions because it might dehydrate that position too. And then putting back, taking out a molecule, a water molecule to create a double bond is not the same as putting back the water molecule in that double bond. That is so much more difficult, especially if the double bond becomes conjugated with something. So what you see here are hopefully reactions that you can use anytime. At least on the paper, you can use it anytime you want, no matter how long your procedure is, no matter how, as long as it's plausible, that will do. Maybe then if you are in the lab and you see that you have a 5-6 steps, and instead you can do the same, this paper does the same in 3 steps, you might want to do the 3 steps instead for the economy of your time, solvents, carbon economy. We don't want to pollute more than we need. But if you know, if you have an idea on how to proceed, that is really good for me. 1,4 are far more useful and far more likely to be found in retrosynthesis than 1,2. Yes, we're using the natural polarity and the reverse of the natural polarity here, but normally speaking, for the 1,4, you might have an alpha halogenal compound, and you use the other carbonyl source in the normal way, exploiting the alpha protons, not the electrophilicity of the carbonyl, but the alpha protons, so that you can exploit the nucleophilicity of that carbon in alpha of the carbonyl. So for instance, let's do this molecule. Where does everything come from? Where does it go? What do you use? What do you disconnect? You have an amino function. You have a benzene, a phenyl substituent. You have an ester. Whenever you see something like that, strategically, you want to think, okay, where do I cut first so that I get the easiest possible synthesis in the lab? We saw the synthesis of the amino groups. amines in general. What do you want to cut first? Let's call it 1, 2, 3, 4, 5. What do you want to cut? I mean, everything more symmetrical, as symmetrical as possible.
Could you do one?
The 1, 5 will do. What do you do to make the 1, 5? There's no 1, 5 dicarbonyl, just this 1, 5 carbon. So it's gonna be pH. You want to put the negative charge on something, the positive charge on somewhere else. Where do you want to put the negative and where do you want to put the positive? As symptoms. What is your most likely nucleophile between these two? The nitrogen is always the most likely nucleophile, so you must have something like that, and that you have your nucleophile. If the other compound has to be an electrophile, you want to put a carbonyl. This reacts straight away, this nucleophile reacts straight away with this electrophile because the other carbonyl here is an ester. Ketone is more reactive than the ester, so this reaction is good. But what are the conditions in synthesis to do that? How do you insert that amino group normally? Consider the mechanism. You have your lone pair here, which attacks the carbonyl. What do you get? Think about possible reactions to make amino groups that we studied. Or just think about, if I do this reaction, what do I get? Nucleophilic attack on the carbonyl, no living group, you get your alcohol. What's next? If you get an alcohol, you might dehydrate, you form a double bond. Is that double bond stable? Yes. What do you do to get to the amine? You need to reduce it down. What is the whole procedure called? Reductive amination. It's one of the most common, if it's not the most common, way to make aliphatic amines. This is an aliphatic amine. It's not aromatic because there is this carbon here. So this one is an aliphatic amine. The most common way to do aliphatic amines is reductive amination. Sometimes you get away with the reduction step and you can do direct amination with some other compounds if there are hindrance factors. But if you are not sure, you tell me or you tell Marcella, because I know she uses quite a lot reductive amination too. You tell us, I'm gonna do reductive amination, so eventually you'll get your double bond, which is gonna be reduced by the most common reagent is sodium cyanoborohydride, but actually any other reducing agent probably will do, unless they mess up with the rest of the reaction, with the rest of the retrosynthesis. So the first one is reductive amination. I also use, normally I do put some this carbon nitrogen on top, but I don't expect you don't have to do that for me. And I think also Marcella says, I will use that, but I don't, so you don't lose any marks if you don't specify that, because when I see here, to me, it's clear enough that you know that you're gonna see ion disconnection. I don't really have you to specify that. You're already specifying it. If it's correct, it's good enough for me. Now you need to do the 1,4. Because you have your 1,4 dicarbonyl species. So once you do your reductive combination, which is probably whenever you do carbon nitrogen, whenever you can disconnect carbon nitrogen bond, please do that. Then once you do that, you have to do that 1,4. How do you do the 1,4? There are not many ways you can cut basically only here to do the 1,4. But you can choose where to put your alpha halogen or your carbonyl. Probably the easiest way would be in this case to put the alpha. I forgot the halogen here on the other side. Sorry about that. But I just put a skin on. But in this case, probably you want to use the phenyl acetone because it can analyze only on one side. You don't have any chemoselectivity or regioselectivity problems. The only problems the only problem you might have here in synthesis is what? Which you always need to consider. Not necessarily for the retrosynthesis exam, but when you're in the lab, you need to consider that. This one is really, really good at self-condensation. So you might need to either activate, you can activate your carbonyl using, let's say, this amine. This is something that we've done in the past. You get your pH. This one goes here, and this one acts as a nucleophile, exactly the same way as you will do with your alpha protons. So if you do that, this will block the elevate the same way as you put a base and you put a phenyl ether, for instance, and then will take uranolate. So you want to have uranolate only so that this one does not react with the sun. It reacts only with your next compound, which of course here, the only thing is missing is a potential living group. You get the choice. Again, also for the exam, if it's, for instance, your final molecule, if you tell me living group, it might do for me. Of course, if you put a halogen or a tosylate or another ester, it's probably more likely because you don't buy from Sigma Aldrich this compound of a living group after you find the molecule itself. But for the exam point of view, it might do. Okay. Let's finish up with 1,6 dicarbonyls. This is a reaction that is called reconnection. It's called reconnection because you actually start from this 6-member ring and you open up the 6-member ring to have your 1,6 dicarbonyl relationship. So when you do in retrosynthesis point of view, basically you have to start from the 6-member ring. That's why it's called reconnection. You're reconnecting it to a potential 6-member ring, which you're going to open in certain conditions. Do you remember how to open this one so that gives you this is a reaction we have done the first time first year. Osmolysis. You can also use something else. You can use osmium tetroxide, which is super toxic. Not that the ozone is so much better, but yeah, I would probably prefer the ozone anyway. But anything that opens, that hydrates immediately this double bond in both sides, and then eventually oxidizes to carboxylic acid, that will do. Again, let's focus a lot on the 1, 3. When you practice, focus a lot on 1, 3, 1, 5, 1, 2, 1, 4. 1, 6 is more unlikely. There is always something else that you can do instead of the 1, 6. But if you have a molecule like that, you must do a 1, 6 at some level. Or what you can do is you place it in a way that reminds you the same way that we turn and rotate the bonds when we use the solder. You put it in a way that is more familiar to you, and you find that you have a 1, 2, 3, 4, 5, 6. But you also have 2, 1, 2, 3, 4. 1, 2, 3, 4. So you can cut here, and you can do the 1, 6. You have options. So the reconnection will lead you to this one, which in synthesis is going to be a ring open with ozone, for instance, or osmium tetroxide. And you get your target molecule. But also can come from, this one can come from the solder. Whenever I see a 6-member ring with a double bond, or a 6-member ring aliphatic, in which you may put a double bond and then you remove it, you hydrogenate, think about a potential deal solder. So here, in synthesis, deal solder with these two, really good. Diene doesn't need to be activated. The dienophile is super activated by 2-carboxy, 2 strong electron withdrawing groups. So this reaction in synthesis works really, really well. Then on the 6-member ring in synthesis, you ring open everything with ozonolysis, you create your 2-extra carboxylic acid. There is always a 1,4 possibility as well. You may need to protect everything as esters because when you do 1,4, you need to use the base. And when you use the base in the presence of carboxylic acid, in retrosynthesis, it's fine. In synthesis, you need to turn base starts with that, with the ester. If you want to do that on synthesis too, on retrosynthesis too, sorry, it will do with me. But definitely, you need to do that on synthesis. You need to tell me, I will not use that carboxylic acid on a base taking the alpha protons. No, that will take the carboxylic acid proton first. That's really important. And then you can do 2 different 1,4. That's a possibility. I will say that this is one of the cases that I prefer using the reconnection to the 1,6 because there are potential problems in this one. Despite it may work, there are potential problems. Can you spot one potential problem on this one, which needs to touch first here and then on the other carbon? What is the easiest potential problem you might spot? You put 2 equivalents of this one to create this intermediate. I'll give you the first attack. You tell me what is the potential problem. What does this B minus do? It's an alpha proton. You can take it from here, you can take it from there. So you might have, despite this one is more accessible, this one is still available. Depending on the base you're using, you might have this substitution here instead of that. Instead with the reconnection, you don't have the same problem. But again, you might get away with that because this one is very hindered. So I have very little amount of density. And most of the product, major product, could be your desired product. But if you are on the paper or the exam, I will accept them both as good. But if you want, you might specify in writing, yes, this one can do potentially also attack here, but actually I think that the hindrance will play in my favor, which we'll probably do. If this one had carbon here, I would say no way. This reacts here. This protein is far more acidic. But in this case, they are equally acidic and one is more hindered. So you probably get away with that. Of synthesis, they are colder, easy. You can start from the dicarboxylic acid, you can start from the anhydride, and then you ring open. This is what I will do in the lab. This one is commercially available, nice and easy, ring opening is super easy. So the result between these two is a very simple reaction. But on the exam, if you start from the dicarboxylic acid, it's totally perfect. Right, the 1,4, yes. We said that. First attack on one carbon, next attack on the other one. Then you, of course, you start from all the ester groups and you need to hydrolyze everything. Which is also a potential problem. It's also a potential problem because you have a potential plethora of other side reactions here. Let's say that you take one proton here, one ester group here, but then before he hydrolyzes this one attacks him for forms of five membrane, the same way as usual on the succinate anhydride. This might happen. That's a side product. With that 1,6, you won't have the same problem because you are reopening exactly in these conditions. But again, the 1,4 route is as good as the 1,6 to me. Maybe this one is more problematic, but we'll still do. Okay. Questions on that?